Good morning. I have divided the session into three parts. One is the basic concepts in sample size calculation as part one, and the sample size calculation in clinical trials, especially when you deal with the equivalence trials and non-inferiority designs. And how do you do it in survival analysis? Now, I'm going to give you the links. Have they sent the slides to you? I'll show you the links. You'll have to cut and paste the links to browser and see whether we can do some exercises. So you don't have to buy a software to do sample size calculation today, because we have good links to do that. Now, so this is basically that, let us say that we deal with two outcomes. One is the proportions, I say the qualitative data outcome is yes or no. And otherwise you deal with the means and standard deviations. Let us understand that you have a hypothesis to test with, and you know what is null hypothesis, and two-tailed versus one-tailed test. Conservatively, I would say, instead of explaining what is one-tailed and two-tailed test, conservatively, many of the journals will ask for a two-tailed test. So two-tailed test, that the probability of making a mistake is either this side or that side of the normal distribution. And let us fix our sample size calculation with the two-tailed test conservatively, that is better. And what is type 1 error and type 2 error? It looks like you people are well educated on these areas. We'll discuss the concepts, the formulas, and discussions. I wanted to highlight the misunderstanding of non-inferiority trial concept and equivalence trial concept in many of the institutions. And there's a concept saying that if it is an equivalence trial, it needs thousands of subjects. It is not true. That's something which I wanted to clarify. If you take that message home and educate other people, that would be better. And this is because the equivalence trial, when you say the two events are two outcomes, two interventions are going to be very equal, the difference which we are talking about is going to be very small, and therefore it needs a lot of sample size, which is not correct. That we'll discuss about. So this is, let me skip some of the slides. These are all very basics. And we always say that the null hypothesis, the difference is no difference. The difference is 0, or the difference, the ratio is 1, and so on and so forth. There's a philosophy behind why we keep this as 0 or 1, and so on and so forth. You people are familiar with, I don't know how many of you are coming from teaching background, that this is a very important table, 2 by 2 table. And you as a researcher, you are here, and this is the reality, the truth. Truth is not known to us many times. It's not like you do what do you do in diagnostic test. There is a gold standard and so on and so forth. It's not that. So let us assume that we know, we are aware of the truth. So as a researcher, I say the null hypothesis is true. When I say null hypothesis is true, there is no difference between the two interventions. Okay, in reality, there's no difference between the two interventions. Therefore, no issues at all. The issue comes when you say no difference. No difference means that both are equal. And on the other hand, they are different. So this is, we call it as accepting the null hypothesis, there's no difference. And while there is a difference, okay, this is beta error. On the other hand, here you say there is a difference. So in fact, there is no difference here. When you say the reality, there is no difference. Rejecting the null hypothesis, you are saying the null hypothesis is false, there is a difference. In fact, there is no difference. That is alpha error. Okay, that is p-value also. This is very important. And here that we say this power is 1 minus type 2 error. That is, whenever there is a difference, our study should be able to pick it up and say it is statistically significant. We understand that is power. The question is that for any time, of every time that we need to calculate the power or whatever, that is something which we need to think about it. We'll discuss it. And What I wanted to tell you is, once you have rejected the null hypothesis, there is no question of asking the power calculation. Many times people say power calculation means they mean sample size calculation. So once you have rejected the null hypothesis and put your p-value as p less than 0.5 or 0.1 and so on, then there is no question of asking the power. Power has to be very high. Okay. Please remember this. Many times people will ask the power. Can you please give me the power when it is already rejected? You don't have to give that one. The power question comes when you have not rejected the null hypothesis. Because when you say this is the power, that when there is a difference, my study is able to reject the null hypothesis 80% of the time. That is power. Okay. If you have not rejected your null hypothesis, the question arises is that, is it because you have studied less number of subjects? That is where you need to ask the power calculation. Do you understand this? Okay. When there is no difference, you ask, have I studied the right number? What is my power? The minimum power needed is 80%. Have I achieved that power? If it is 60%, that you know that sample size is very small. Do you understand this one? This is very important. Therefore, another concept is, I said type 1 error is your null hypothesis. This is a type 1 error, is your p-value. When you say p-value is p less than 0.5, what does it mean to us? P, anybody would like to comment on this, p less than 0.5? What does it mean to us? Over 90% of the time, it is not due to chance. In other words, that it's easy to remember. Probability of making a mistake is less than 0.5. Probability of making an error conclusion, because we conclude there is a significant difference between the two, that means it could be wrong. It may be an error that is less than 5% of the time. So that is why it is put as P05, not as greater than 0.95. We understand this one. So as the p-value becomes smaller and smaller, the evidence becomes larger and larger. Is that clear? So rejecting the null hypothesis when it is true, rejecting the null hypothesis when it is true, that is in fact no difference. But we said there is a difference. If at all my conclusion is wrong, that is less than 5% of the time. Is it clear? So therefore, this is a very important concept. On the other hand, type 2 error is accept the null hypothesis. Accepting the null hypothesis when it is false. So we are saying that there is no difference. In fact, there is a big difference. There's a lot of examples in the studies. Later on, the studies have come out with the significant difference between the two interventions and so on and so forth. So this is where you ask the question, have I studied the right number? The type 2 error is associated with the sample size calculation. Okay. So when I present some examples, you should tell me that this is the problem here. Okay. So therefore, the power is the complement of type 2 error. Whenever there is a difference, my study should be able to pick it up as statistically significant. That should be over 80% of the time. Is that right? Okay, that is the power. Power calculation is done whenever you have a negative results. That means you are not able to reject the null hypothesis and you calculate the sample size, power, and see. Slowly, I'm going to introduce this. So now the question is, this is the study which I'm going to discuss this with you later on. Let me introduce this concept of the study. The government wanted to know whether we can train community health workers who could treat psychiatric morbidities, because it's very difficult to get psychiatrists work in the community, rural area. So already they are very rare, and ask them to go to community, it's very difficult. So therefore they thought we'll train the community health workers for 6 months, treating common psychiatric morbidities in the community, and compare them with the psychiatrist. So therefore, the patients were randomized to have to go to community health workers or psychiatrists after training, after you have trained community health workers. And therefore 35, someone suggested 35 patients, so totally 70 patients, 35 should go to community health worker, 35 should go to psychiatrist. These are all the results. What is the cure rate, optimal cure in community health worker arm? 40%. And in psychiatry group, this is 63%. What does it suggest to you? It suggests that the optimal cure was very high in psychiatry as expected in the psychiatrist. The difference is 23%. No, this is by mistake. Okay. This is, now it is not statistically significant. The ministry started jumping. So we achieved our goal. Now, what is the null hypothesis here? There is no difference. Community health workers are as good as psychiatrists. You don't reject the null hypothesis because it's not statistically significant. Therefore, how do you conclude? You don't reject your null hypothesis, accept the alternative hypothesis. Sorry, accept the null hypothesis. We don't reject the null hypothesis. So they have accepted the null hypothesis. What is a null hypothesis? Both are equal in effect. So therefore they said, okay, we'll train community health workers for 6 months, let them treat the psychiatric morbidities in the communities. So when you look at here, the moment, as I said, there's no difference between the two arms. So for statistically, there is no difference between the two arms. You should ask the question, have they studied the right number? Calculate the power. The power is only 39%. So let's say 40%. Still 40% has to be there. So therefore, they should have studied, I worked backwards and saw that they should have studied 70 subjects in each arm, not 35 subjects, to have 80% power. Do you understand? If you have access to this number, please remember this 40% and 63%. We'll do the calculation and see what is the number we need to have in each arm. So who picked up 35 subjects in each arm? Just like that. Let us study 30 subjects. Drop out 5%. So 35 subjects in each arm. So we'll do the study. This is a big mistake from the ministry. Okay. And there's one more message coming out of this study is that if you don't reject the null hypothesis, don't ever accept the null hypothesis. There is no concept of accepting the null hypothesis. Okay, this is, then how do you prove one is as good as the other one? So we have equivalence studies and non-inferiority studies. Writing the hypothesis is different and so on and so forth. I think Kant introduced it yesterday, isn't it? Do you remember? We'll reorient that equations again. Not equations, it's a hypothesis statement. Somebody said too much of alpha, beta, and so on, delta, etc. Okay. This is the formula. This is the Z value. This is for type 1 error. Alpha means type 1 error. Beta means type 2 error. So usually this is how we write the equation. And this is the event rate in arm 1 and the event rate in arm 2. Q is complement of the P1 or Q1 and so on. Q is complement of P. Is that okay? If I say with the 10% cure rate, 90% no cure. That is how you just substitute the values. Basically, the D tells you the difference between P1 and P2. Many times in reality, when you start the study, plan a study, you have only one intervention in your arm. You know about that. Say, for example, the event rate or whatever. So when you want to bring in a new intervention, add something more into the intervention, you may not have the data. Mostly 90% of the time, my boss used to say that 90% of the data is available. People are very lazy to pick it up. You don't go and pick it up from the library. So let's say there are occasions you don't have that kind of data. then you have to negotiate. I'll be happy to have this intervention extra added to the existing intervention if there is a 10% more event rate or 15% more event rate. So that you need to negotiate. So supposing this is 10%, P1 is 10%, say for an example, of 80% cure rate. And you say this would be 90% cure rate. You added it 10%. It comes from you. So therefore, this is 10%, the D square is 10% square. Okay. And this, this is standard values that alpha 0.05, it is 1.96. This is 80% power 0.842 and 90% power 1.282. So this, the standard values. If you don't have access to formula and so on, so software, you can do it manually. It's a very simple calculation. This is a study which I spoke to you yesterday about the pralidoxime study for organophosphorus poisoning. This is one of the PG sometime back, many years ago, maybe 30 years ago, he did that study for medicine 2 department where Tambu belongs to. This is the data. I just wanted, I am not going into the details of what is the null hypothesis, whether equivalent study or non-inferiority. The data was given to me in those days, asked to calculate sample size. 34 subjects, 24 subjects and in each arm. So you calculate the sample size. It suggested that you need to have 121 subjects in each arm. Please remember, this is 121 in each arm. Those days, we used to get 45 organophosphorus poisoning patients per year in our hospital. So how many years you need to do the study? It's a big number. Where else I can do the massaging so therefore I can reduce the sample size? I can bring in, this is 80%, this is 90%, 1.282. This is beta error is 10%. So I can make it as 80%, isn't it? That will reduce my sample size. Instead of 1.28, if I put 0.842, it will reduce my sample size. And instead of saying that, say for an example, you can say, this is the difference is, let's say 12%. You can say we might reach 15% also, who knows? You can change the difference because the data suggests that you can, the next alternative is a scenario is, we would aim for 15%, though the data is suggesting 12% and so on. So you can reduce a little bit or increase it a little bit so that you can taper the number and see whether, otherwise you need to go for a multi-country studies. Now today we get a less number because there's one more medical college in Vellore that all the poor patients go there. So you need to see how we can reduce this number. And there's no hard and fast rule that you have to stick on to this number because already the data is from small numbers. Any questions? This one. This is something wrong. Plus, not minus. Yeah. And you need to introduce a bracket in between. So put the bracket in. Okay. This is when you have continuous variable, we deal with the standard deviation, it's variability of the data. Again, the problem is looking for the variability of the second arm, which you are proposing. The t-test, the sample, the formula are derived from the t-test and proportion test. One of the assumptions is that the variability has to be same in both the groups. Please remember, it's a very important assumption in t-test and any test, two-group test, t-test. The variability has to be similar in both the groups. That is where we are deriving that formula from the t-test concept. So therefore, if that is a concept, then if I have one group variability, I can use that variability for the other group also. Do you understand? You should not get stuck with that and saying that I don't have the variability. Use this variability of one arm which you have in hand, or generate data and estimate it and put it in the formula. Otherwise, this is instead of PQ, we are using this variability standard because of this Y2, because there are two groups. we have. You understand? There P1, Q1, P2, Q2, two groups. Here we are saying the same variance, therefore two groups, two times the standard deviation square. Any questions here? This is how you need to understand this. The difference between mean 1 and mean 2 is your d square. Okay. You have the flexibility to increase it or reduce it a little bit so that your sample size can be changed, not very much. Okay. So this is just if I have the duration of stay in this is something else, cholesterol level and the standard deviations, etc. Just explain this one. Please copy this link, and if you open your browser, I'll show you. This is very simple. Do you see this one? Sample size calculation. Do you get this one? Okay. Now the next question is that are we dealing with one group or two groups? What is one group calculation? To estimate the single proportions. If you want to do your studies, your interest is to find out what is the prevalence or incidence of something and use one group, single group. Say for example, I wanted to know what is the proportion of vascular headache in my headache clinic. So this is reported to be 30%. So how many subjects to be studied to study the 30% currently? That is single proportion. Do you understand this? What we have is two proportions. If an example that high dose and low dose study, or let's say that psychiatric morbidity. Do you remember the data? Can you please tell me that what is the proportion? 40% versus 63%. 4 and this is 63%. So confidence interval nothing but this alpha error, 5% alpha error. And now if you wanted to have 1% alpha error, then you see 99%. You see here, so there's an option available. And power, I wanted to have 80% power, okay? And two-tailed test conservatively. Submit the data. What come? No need. Yeah. This is the data which you have provided. It suggests that you need to study 82 subjects in each arm, totally 164, but they have studied only 35 in each arm. Do you understand this? Unfortunately, It doesn't give you, I don't know how to work backwards and see what is the power, as I said, 39% or whatever. You can do it manually also. The N Master is a software which comes from our department now. They're marketing it. So you can write to them and they'll offer it for 1,500, which is a very good software. Okay. So when you are here, you can ask for that software. You can buy that software. It's very useful. Say, for example, this is, I'm marketing it for the department. This is N-Master software which we have developed. This is the software. We have two groups, proportions, outcome is proportion, and you have two groups, and hypothesis testing for proportions, two proportions. That is what we are doing now. So this is, if anything about 10% is called a large proportion. So therefore, here our event rate is 40% and 63%. Therefore, it belongs to large proportions with the equal allocation. Okay, choose that one. Now input your data. Say, for example, proportion in this one is a 0.4. This is 0.63. And estimated difference is this. The gray color area, meaning it gets calculated sometime. Okay, that you don't have to input any data into that. So for example, here 80% power we wanted to have, and alpha error is 5%, two-tail test. So it says 73 in each arm. You understand this? It's very easy. If you wanted to negotiate instead of two-sided test, let me have one-sided test, it will reduce your number. So if you put, say for an example, one-sided test, so 57 in each arm, 60. Okay. As I said, this is, now if you wanted to know about help, IRB wanted the reference for this formula and so on and so forth. So this is the formula which is given to you. There's an example here, there's a reference here, and so on. You can copy that one. 1,500 is just a dinner cost, so it is very cheap today. And you can, yeah, there's various scenarios you can put. 1 minute, I'll show you. Supposing here 0.4, various scenarios, 0.4 and 0.63. This is calculated, and instead of 80%, you put 90%. 5%, two-sided, 97 subjects. You give various scenarios. What we do here is we talk to the PG and put various scenarios and copy and paste it. You can save it in Excel and you can save it in Word, copy as a table and put it in the IRB proposal. And highlight what you have chosen as the number, correct number to be studied. So they are convinced. So do you understand this? This is how we do this one. Now, this is the question is now I wanted to calculate the power because I don't know the existing data is this. The power number studied is 24, 35 in each subject. I wanted to calculate the power. The 35 in each arm with 5% alpha error, two-sided test, 62. Power is 62%. But if I put this one as (49% the power. So you can calculate the power. You can say in my when you review the journals, we do this one. So if there is a negative results, and tell the readers, reviewers, editor, that this study has only 30%, 40% power. It is not because there is no difference, and so on. So this is about two means and two proportions calculation. This is a simple concept. We should understand what is type 1 error and type 2 error. And when you choose two-sided, conservatively two-sided test is better, and so on and so forth. And it is not dropout adjusted. So you always incorporate some amount of 5% or 10% dropouts, and so on and so forth. Any questions? Yes, sir. No, perpetual. You can use it forever. Don't give it to others. Okay. So you can contact the department. You say you are from academic institute, not from industries. Academic institutions, you are from academic institutions. And they'll give you the details. Madan will give you the details. You can talk to them. Your guys are there. The students are there. You can talk to them and they'll get you this. Okay. You can tell them that they'll give you a new copy. So this is what we have discussed. This is a very important statement. I said there is no concept of accepting the null hypothesis. So I presented this in Trivandrum once. There's no concept of accepting the null hypothesis. Big epidemiologists started fighting with me. How do you prove that 1 is A is equal to B? At the time, it was not evolving, or they have not read about it. So this is from R.A. Fisher, the father of statistics. This is null hypothesis never proved nor or established. Never proved. Please remember, you can't prove this null hypothesis. So therefore, you cannot accept the null hypothesis. How do you phrase the hypothesis in equivalent studies and non-inferiority study designs, and so on and so forth is very important. Okay. And Tambu was saying that over 90% of the articles in the New England Journal of Medicine are non-inferiority trial related articles. So this is a standard of design or whatever today. So any questions, and then I'll move on to explaining this concept for equivalent studies and non-inferiority studies. So this is very specifically for what we have discussed is meant for superiority trials. So you wanted to say one is better than the other one, and so on and so forth. That is where you take the difference. And so therefore, only the problem comes when you deal with the placebo arm. So the concept is a bit different. I'm not going to talk about it. So this is here, this is Kant also yesterday presented about it. We say And in the superiority trial, we don't specify any margin to say that the difference has to be greater than that margin. So usually it is greater than 0, no difference. That is what we do in superiority trials, to say one is better than the other. Whereas when you have equivalent studies and non-inferiority designs, you fix the margin. Not in superiority trials. Superiority trials deals with, is there any difference between the two arms? That is null hypothesis is 0, or in terms of odds ratio relative risk, it is 1, and it is greater than that. That is all we discuss. We look at it that way. So no delta and all that in superiority trial. So what you do here is, when you look at this, if the confidence interval avoids 0, then it is statistically significant. Reject the null hypothesis. Is that clear? No question. So this is the second option is no significant difference because it overlaps with the 0 null hypothesis value. If this is odds ratio relative risk, it should avoid 1 from the confidence interval. Sir, usually the study also we touched about equivalence trials and non-inferiority designs. We fix the margin as delta. Here there's no such margin in superiority trials. In superiority trials, you wanted to see, is there any difference between the two arms, as I presented just a while ago, or no difference? So meaning that the confidence interval which you construct should avoid 0 in between the two limits. Say for an example, this is a confidence interval of the difference between the two arms. This does not include 0 in between the two limits. Is that right? Therefore, it is statistically significant. Now, let me take an example of relative risk or risk factor studies, relative risk or vaccine trials and so on, where you deal with the relative risk, 1 minus relative risk and so on, or odds ratio. That confidence interval should avoid 1 here. This is 1 because no difference means 1. The ratio of 2 risk equal means the ratio is 1, not 0. When you talk about the differences in proportions, then it means 0. Is that okay? So if it overlaps with the confidence interval, then we say no significant difference between the two arms. So this is the formula which we are talking about. Just a while ago, I put this as d square in the earlier formula. So the difference between the two interventions, two means. And you remember I said the SD square. So here I used the notation sigma 2 times. So when you deal with Madam Rice, the plus or minus, this is plus. This is. Any questions? These are all some examples which we have. Now, say, hello? Which slide? Goal to compare new drug therapy with this. However, it may be possible that for some intervention, we wanted the difference to be greater than a pre-specified value. So it's very rarely you set it up. Sometimes a lot of questions yesterday it was raised. Sample size is very large. The effect size is very small. Because of sample size, it is statistically significant. Do you understand this question? Which you clinicians will say, what is this? This is a very small, insignificant clinical difference, but it is statistically significant. So if you are very uncomfortable with that, you set a margin. The clinical difference has to be greater than 5%. Or do you understand this? If you set the margin and you are saying that as like the delta, your confidence interval has to avoid that this thing. Instead of any difference which is significant, you say it has to be greater than that. So that is how we fix this one. Yeah, that is better. Many people wanted to show there is a difference, irrespective of the small difference, clinically important difference. But I don't know whether you get criticized and all that. That is different. Yes, sir.
I don't know if it's the right place to ask this question, but what is how do we arrive at the reasonable effect size? Because this is being said quite that effect size may be important even though statistical significance does
Yes.
not exist.
Yeah.
So reasonability of the effect size, how do we arrive at that?
Any suggestion, Kant? Yeah, yes.
That's a crucial question, right? And for superiority trials, you're trying to show that your new intervention or whatever compared to the standard of care is better. So you should know what is the effect that you think exists, what is the proportion that you will observe as a control arm. So that we have to research, let's say the proportion of people that do better. Control arm is 20%. Now the question becomes, what would you like to be the effect to detect about your new intervention doing better? Obviously, if you got 40% in the intervention arm, you would be extremely happy, right? It's 20% better. So now what you have to start to imagine is, what would I, as the investigator, be comfortable in observing? So I usually, as a statistician, I'll meet with the investigator and I'll get them to think about this and say, okay, what if you get that 40% in the intervention? Would you be happy? And you will say, oh, yes, fantastically. Then I will say, well, what if you got that the new intervention gave you not 40% better, but gave you 30% better? 30% versus 20% in the control, it's only a 10% better. Would you be happy? And now you start moving your head. Maybe. You start saying that. But then I will push you and I'll say, would you be happy? Suppose at the end of the day, you've invested 2 years of your life doing this trial and you got 30%. Would you want to be able to say that's a meaningful improvement from 20%? And you'll say, yeah, I can convince some people that that's meaningful. Now I will even push you further and I'll say, okay, you're happy with 10% better. What about 5% better? Oh, no. 5%, it's not good. So now between 5 and 10%, I'll say, what about 7%? Now you keep, now this business continues and you move your head. No. That's not good. Then 8%. No. 9%, maybe. Then I will do it for 9%. Because why? Because I will get you the necessary sample size so that at the end of the day, if you get 9%, you would be able to claim statistical significance. Because we don't want you to say, well, I'm going to plan the study for a 20% difference. I will get very small sample size needed. I will get maybe 15% better, but and that's fantastic, but you don't have the power to claim significance. So what I'm trying to do is protect you. And that's why I want you to determine what is the smallest superiority difference, that little delta that we had, that would make you comfortable in saying to your colleagues, to your peers, this is an improvement. But you see that it's not the statistician deciding it. Yes, it has very strong implications on sample size, because going from 20% better to 10% better, 10% better will be a large sample size compared to the 20%. But going down to 9, going down to 8 will increase it dramatically because it's in the denominator and it's squared. So it really has a big impact. But the way to determine it is you yourself going through this mental exercise of what will I be comfortable telling my colleagues in my discipline that this is superior because it is this much better. Okay, that's
Because it has got very huge implications.
totally.
Even with even if we have 10% improvement, but the cost is 10 times more, then whether it is good enough. I'm talking about the example of
Yeah.
rheumatology only.
Yeah.
That infliximab injection versus something which has come 10 years later, the cost difference is very. The outcome or improvement may not be so much, but so
No. So I think there. So now that becomes the more complex, pragmatic thinking about how do I choose these things. When we are talking about choosing a delta in the abstract, we're choosing it from a purely statistical standpoint of what is important to you and its impact on sample size. But we also need to consider not only the efficacy or benefit, we have to consider the risks and we have to consider the economic risks of saying that this is better. And so that there isn't really a good way of doing it. It's all very subjective that you would say, yes, because it's infliximab is very expensive, I would not want to say that it's better for a small thing. I want it to really be bigger. I want the effect size to be bigger because it's going to cost so much. And now I say, I'm not going to come down to 10%. I will come down to 15%. And if I get 10%, I will not say that it is better because I don't think it is from a practical standpoint, because 10% better but costing a whole lot more is not good. But this is not statistically decided. This is decided by you incorporating everything. And so we work in cardiovascular disease with mainly trying to prevent MACE, and we deal and all of these problems. But we look at anticoagulants. Anticoagulants cause bleeding also. And so now we have to come up with what is the meaningful effect given that we want to tolerate some amount of bleeding. And so that's the kind of stuff that, you play around with it in your mind, but then we can use the software to see what is the implications on sample size by doing what Professor L.Jeyaseelan is saying of seeing the sensitivity analysis to different choices.
Yeah. A related question. By looking at the sample size, can we calculate the effect size from reverse calculate the effect size? Because the journals always mention the sample size. Nobody mentions the effect size used for calculating that.
They do.
When you write in the sample size section, you say, we designed a study to be able to detect the effect size of such and such with this much power, this much alpha, and two-sided test requires this. So that usually should be. And then the effect size, how did you determine the effect size? The effect size is something that you determine from what I know is the effect in the control arm, because of the past literature. And what do I think my new intervention is going to achieve? How do I come back from phase 2 studies, phase 2, 1 studies, and I know something about the effect. So you estimate that, and then you say, well, I think it's going to be big, it's going to be small, and I want to be able to, if it's this size, I would like to be able to. No, that will become very happy. Right? With the smallest time. So you were happy because you got a big effect. Yes. You are sad because you spent more money. Yes. That the B that he had in the denominator is the delta.
Difference between the two. Yeah.
So which means that we are actually putting that margin for all these.
Yeah. Yeah. Yeah.
I think that maybe
No, no, but you have to choose that.
yeah, you have to do better.
It is the, well, okay, no, it's the effect. Effect size is usually that divided by the standard effect.
Yeah.
But I use little delta and he uses little d because I want people to hire me, that's why I use Greek letters. Because I use Greek letters. Yeah, that is it. Yeah, most people bring it in later, because it's, first of all, as you say, it's not that clear what it is. And also many people will have to decide on their own whether it's efficacious or not, given the cost of it. Is it worth doing it? That's a personal decision. It varies by the socioeconomic level of the person, the resources available in the country or state, and all sorts of other norms. So it's not usually incorporated into calculation. Plus, there isn't a good way of incorporating it.
They don't have the money to recruit so many patients. I have $100,000 to recruit the patients. What is the required sample size? We do it in the reverse to make sure that we have an adequate sample. If not, change the outcomes, increase the event rates.
One of the things that we'll be talking about in the afternoon, which we did not get to talk about yesterday, is the choice of outcome. The choice of outcome will determine what effect, what efficacy you will have. And so it will definitely determine or impact your sample size. So we'll talk about the outcomes. What people need is, depending on the type of outcome and effect you get with an outcome, people choose outcomes that give them large effects, so they don't have to have a big enough sample size. We create composite outcomes because we have more events and requires less samples. So there, we'll talk about this after lunch.
Okay. Yes, Tambu.
The comment that what we notice is we do critical appraisal. I'm loud enough.
Yep.
People will choose an outcome for sample size, give them the lowest sample size. Let's say a continuous outcome and mean difference. But if you look at the primary outcome, it will be something different. But actually, a sample size should be chosen based on your primary outcome, not the sample size.
Is
The
it
smallest sample.
smallest?
That's the way many people play when they come to this. That's true. You first write your PO statement, what is their outcome and when it will be collected, and then the sample size based on minimal clinically important difference of that. Not game the system that, okay, I'll put the secondary outcome as a continuous outcome, but use that for my sample size and hope nobody sees that that's not my sample size. That's what many people.
Yes.
We had one class 2 days back in India. About the pricing of the treatment. So, argument they had one figure appraisal, one trial, where they were comparing the normal saline vaccines to previous, I guess. So, as a result, they found that there is no clinically meaningful difference in the primary outcome. The cost was the common. So, the CJ administration now has to take that whether they are ready to put that cost for the patient. To use that.
Okay, you are.
Sir, respect to a pilot trial, in those situations, how would sample size and interpretation of those?
So we'll talk a little bit more about pilot trials and vanguard trials. But as I mentioned this morning, pilot trials are really for feasibility. The outcomes of a pilot trial are not the outcomes of a large trial. They are to inform the planning of a large trial. That's why it's called a pilot. There's other things called Vanguard studies, and we'll talk about Vanguard, which are internal pilot studies. And you can then do different sample sizes for that. But for example, when you're doing the calculation for sample size, you're required to know the variance. And if you haven't done this before, where do you get the variance? You a pilot. You don't know the effect. Then let me do a pilot and get some estimate of the effect that I can then put into the formula for the other. So there's a lot of things that you get from a pilot is the estimation of parameters to go into the calculation of the sample size. Also, can I recruit? Can people follow up? I don't have losses of follow up. Do people tolerate the medication? Do they have too many adverse events? Those are things that may not have been seen in phase 2 trials, but now you're going to see it in the phase 3. So people do this to make sure it is feasible to do a large trial. Also, they do them because if a funding agency says, how do you know this is going to work? We not have any experience with this. Your pilot said, listen, we can do a study. We did the pilot. We have experience. We know it's going to be feasible. Give us the money.
Pilot study, the sample size, then we.
So the pilot, what is enough? Yeah. So what the sample size for that is usually done 2 ways. One way is, as L.Jeyaseelan says, somebody said, 30. They just look up and God tells them 30. That's usually what people do. But the second way is a better way and say, oh, I want to know the effect size. I want to estimate the effect size with some amount of precision. And we can do a sample size for not for power, but for precision. I want my confidence interval to be plus or minus 4%, or plus or minus 1%, or plus or minus 10%. If I wanted 1%, I need a bigger pilot study. If I want 10%, I need a smaller. But we can calculate this. It's not, looking at the heavens and seeing what God tells you you should do. There's a different formula for it, but there's formulas for all of these things. Every software for formula.
That link, a single group is the precision. That totally. Yeah. Precision comes from you. Okay.
So after lunch, we're discussing outcomes. That's one of the questions. When you have multiple outcomes, you have secondary outcomes, you have tertiary outcomes, exploratory ones, you have composite outcomes, when you have hierarchical outcomes, all of that we're still having to discuss. You can calculate sample size for all of them if you wanted to. Even for subgroup analysis, even for interaction tests, even for everything, and then take the worst case scenario if you wanted to do that, and then you spend the money for this. But no, but most people do it for the primer. That's why it's called the primer. So yes, you may have multiple outcomes. Many people have multiple outcomes. In fact, almost always you're interested in more than just the primer. And so yes, there is a whole set of considerations when you have more than one outcome. And we always have more than one outcome. But we judge the efficacy of the intervention on a primary. That's what regulatory agencies will demand from you. But you are free to calculate power and sample size for everything you want to. We'll talk about that in the end.
This is about equivalence trials. So that we discussed about bioequivalence and clinical equivalence and so on and so forth yesterday. This is the goal is that the difference between the two interventions are within the falling within the pre-specified margin. Okay, then you say they are equal in effect. Now, this is what yesterday that this is what we say the pre-specified amount is noted as delta. The difference is delta usually. So this is basically, some people criticize this, the way we write the null hypothesis and alternative hypothesis. We said, because you interchange the way you write the hypothesis doesn't mean that you are all right in science. It's a good criticism. Do you understand this? Is when you say usually the null hypothesis is no difference between the two arms. Okay. Here, let's see what are we saying. This is the difference between the two arms. The new treatment and the standard of care treatment difference that is greater than as pre-specified values. So this is false here. Greater than this goes outside the delta. We are saying that the null hypothesis is they are not equal. It falls away from the delta. On the other hand, here in the alternative hypothesis, we are saying it falls within this delta. Do you understand that? It comes within the delta. This is delta. This is, say for example, versus, sorry. This is the difference between the two treatment, which is, this is your minus delta. It for below than the minus delta. Versus the alternative hypothesis is that it is greater than the minus delta. That means you fall here. Is that right? And the alternative hypothesis, this is that versus alternative hypothesis. And this is another way of writing it. Okay. If it is yesterday you spoke to you about the negative benefit, positive benefit and all that. That is how it is. So what are we saying in the first null hypothesis itself? Yeah. When I say this is not equivalent. This is not equivalent because it exceeded the delta margin. Okay. So we are saying not equivalent. That is usual null hypothesis. What we say that there is no difference between the two groups. Here we are saying that this null hypothesis is not equivalent and alternative hypothesis is equivalent. Okay. Someone said, you people rephrase it in such a way that you bring the alternative hypothesis as null hypothesis and so on and so forth. Now, this is how that it has been phrased. I don't want to go into the philosophy of it, or I don't know about the philosophy of it, rewriting it like this. Let us. No, I'm just giving you one. It is greater than one side. This is. Say, for example, if one end exceeded the delta, the equivalence is broken. So you don't have to go into the both sides and say it out. One side, say for example, if this margin exceeded this, comes here, then it is broken. Okay. So therefore here you say whether it is greater than that, that is not equivalent. If it is within this one, it is equivalent. This alternative hypothesis suggests that equivalent. Okay. So if you look at this as a layman, that in the usual hypothesis writing is you say equivalence is no difference. So that is how we usually write for superiority trials. That somebody interpreted this as you people wanted to rewrite it in such a way you according to your convenience and so on and so forth. Okay. Because people don't like this kind of study designs. So therefore, we say the null hypothesis is not equivalent and alternative hypothesis is equivalent. Okay. Is that simple? Okay. And when you say this is, you take it as a difference, whether the difference is less than the delta, that means this is the negative sign, this comes to the side. And or exceeded this side, this comes here. That is alternative hypothesis. This is what 1980s, 90s is very much available in industries, and they were using it to prove one is as good as the other one. But not the way you, if no difference, you just say that A is equal to B. That is not correct way of accepting saying that there is an equivalence. So therefore, if you look at this one, this is equivalent. This side, the left side has exceeded this margin, therefore not equivalent. And here is not equivalent, and this is not equivalent, and both sides has exceeded this. Now, supposing that this is, say, for an example, this, yesterday he had shown you that yesterday he had shown you that this is what we are talking about. This is plus delta. Can you see this one? Now, supposing the difference in margin is like this, what would you conclude? Can it happen? What does it suggest? It can happen. Superior. Why superior? So this is super superior. Superior. Superior because it avoids zero in between. Anything which avoids zero in between. So it is superior. Do you agree with me? So what we are saying is equivalence is that this is equivalence. Okay? Do you agree with me? So this has to be, so you just, very simple concept, plot your confidence interval and see where you are. Where are you? This has to be understood very clearly. Now, this is equivalence trial. Now, this is, now there is a concept I wanted you to listen to me very carefully. When you go back to your institution, there may be a lot of top level epidemiologists who will object to it. And you say, this is minus equivalence trial, I'm going to study 50 subjects in each arm. They say, no, you're wrong. It can't be 50. Because you're talking about equivalence means small difference between the two arms. Your number has to be phenomenally very high. That is a kind of argument they'll have. Do you understand my question? If the difference is equivalence means we are talking about the difference between the two arms is very small. Therefore, very small difference will demand a very high number. That is a concept which they have. What they do not know is, this is what they are talking about. This difference is very small. Therefore, it has to ask for a large number. They forgot the fact whether that difference is coming within the delta. This concept is not known to them. The calculation is ignored completely. This is what you will have to explain to them. Okay. So they have no idea about it. Their common sense says that there is a small difference between the two, and therefore your sample size has to be much higher, as we do it in superiority trials. In non-inferiority trials, the question is you have fixed your delta. That difference comes within the delta. That is a question which we have to have. Therefore, the sample size calculation is, that depends on this, whether this difference falls within this. There is a book by David Campbell, and I forgot Machin and David Campbell from Southampton University. We have the book in our department. You can visit and see that book. There is a statement which says, in occasions, you can take this as 0. Because we are saying that both the arms are going to be equal in effect. That is a null hypothesis which you have. The hypothesis, the premise which you started the study. Therefore, it can be 0. If that becomes 0, what is your sample size calculation going to be? What? Delta square. It's like as good as your superiority trial. Do you understand? So number cannot be more than your 1,000 or 2,000 as the other epidemiologists claim that. We need to understand the basics. So therefore, you don't oblige to them and tell them that explain this concept to them. Just quote that book. So whenever you do, I'll show you a calculation. There's a New England journal I told you about. We got involved with the measles study vaccination with the 2,000 children. So we calculated the sample size, putting that difference as 0. Then you are interested only in the margin. What is your margin? Equivalence margin. You understand this? Yes. No, we will come there. We'll come there. So it will be similar. I'll show you the formula. So please remember, this is not understood. So as Campbell and this group, Southampton University, Machin and Campbell et al. Have said that because of the premise with which we started the work is 2 arms are going to have an equal effect size. That delta, the difference could be made as 0. You are interested in only the margin. And it becomes a number is going to be as good as your superiority trials. Okay, we'll see some examples. If we have difference, we have the data, mean, effect, put that calculation and see. And so what kind of number you get. So this is one small example to show you what kind of number which we have. Okay, the difference is, say for example, difference in means is 8. Expected mean difference is 0, 6, and so on. This is to explain to you how this calculation is done. This is for the proportions. And this is the, if you work with the sample size, your NMaster software, this is what you need to do. Let us do this one calculation using this link. Copy that link. So non-inferiority trial, maybe that we'll see. There's one at the bottom. Just copy this one. Another. Can you copy this one? I don't know. Binary outcome, power calculators. equivalence trial, non-inferiority trial, and so on. Let us take binary outcome, equivalence trial. Significance level 5%, power is 80%. Let us make it as 80%. So percentage of success. Let's say percentage of success is 30%. Percentage, therefore 30%. And equivalence limit difference. See, this formula doesn't ask you what is the event rate in one arm, what is the event rate in the other arm, and so on. It assumes that there is a difference. It is asking you the delta and the event rate. Because the event rate is going to be same in both the groups. You just give one event rate.
Both control and experimental, but what is it control?
Yes. Okay. This is, let's say for an example, 10%. Now tell me whether number, if I have a 5% margin delta or 10% margin of error delta, which one will give you a higher number? How many people are voting for 10%? Which will give you a higher number, 10% or 5%? 5% will give you the number because the 5 square is smaller as compared to 10 square, the denominator. Okay. This is sample set per group is 360 and therefore this. Okay. Do the same calculation. Yes. 30%. That is a assumption which we have. There may be small differences. If there is a small 25% versus 30% in your actual data from the literature, put that values and calculate the sample size. It will reduce the sample size to some extent. Do you understand this? This is basically if you assume that the both are going to be equal in effect, it is as good as your superiority trial because you fixed your margin. Any questions? So these are all very simple calculators you can use. Yes. Do a pilot study and estimate it. No, let's just say the literature should have some are nearly equivalent to that outcome and get the data and say it out.
I just wanted to reiterate, when you're doing a clinical trial, you have prior information. You don't, the first thing
Yeah.
you do on a research question is hardly ever. There should have been observational studies, give you some information. You should have been phase 1 studies, phase 2 studies. You know a lot of the stuff that goes in. You're not just making up numbers and doing this as a person. You have all of this knowledge. Well, if we don't, like when COVID came, we had no idea if they were going to work, but we wanted things to work. Said, well, it's a good, should be anything better than placebo. The first thing, the hydroxychloroquine, anything better than placebo. People dying. Well, but we have some idea what people are dying. Those studies may have been poorly designed because they were not very precisely known entities to put into this. It was better than that. But once you know something, now you know what to put in. Once they got something to work, that's the microscope. Now the new things have to be tested against. But they knew already previously what the control on. But this is it's an iterative process. When you study the clinical area, there's lots of information. There's almost nothing that has no knowledge about what's happening. When HIV appeared, there was no knowledge. When COVID appeared, there was no knowledge. But you can name almost everything, there is some knowledge about it. There's a lot of good knowledge. what is the referral rate for now? So you can take some data. What is the referral rate now? That's just a quote. So you know that. You should know that. How much you want it to increase it is your choice. But it doesn't matter the ChatGPT or not. You know your outcome is referral rate. You should know what the referral rate is now. If you don't know that, you better study that first. Because how do you want to know if it increases if you don't know what it is?
Okay, shall we move on to non-inferiority trial? Okay. And we'll do an exercise. So show, this is, I'm using a Kant slides. Show effect of a new treatment on a certain endpoint is no worse than that of an existing treatment by more than a pre-specified amount. Okay. So therefore, you fix the margin and you say that the difference is not more than that. So, okay. And say for example, the example which I told you that we got involved with, the subcutaneous arm versus aerosolized vaccine, 2 arms. The vaccine efficacy is 95% in the subcutaneous arm. Otherwise, we hypothesized because we have no data on aerosolized arm. It should be similar, but it cannot be similar. But you fix the margin. So the margin has to be decided whether you want to have a margin of 10%. When you say margin of 10%, what does it mean to you? When the efficacy is 95% in the subcutaneous arm. We are saying 10% margin means it should not be more than, the difference should not be more than 10%, means the worst effect should be 85%. Is that right? The worst efficacy is 85%. It should not be more than that, means it should not be 80% or 75% and so on. Is that clear? Now, therefore, this is the same concept. Don't worry about it. This is the margin. If I study in the aerosolized vaccine study, this is 10%. Say, for example, this is 10%. What we are saying, the difference between the 2 arms, it is established data is 95%. So this is the next arm, that is aerosolized form, should have at the maximum 85%. The difference is 10%. So this, if that exceeded, the difference in confidence interval exceeded the 10%, you say it is inferior. Okay. Here, this is, you're saying non-inferior because this lies within this. It's a very simple concept. Now, this is a formula. This is the same formula which we have used in this thing. There we use modular sign because to get rid of the negative sign or whatever difference. This is, you have the link with you. Can you please do this example? Zero conversion at 91 days would be around 90%. This is your P. Okay. Or we would conclude non-inferiority when the subcutaneous arms conversion, zero conversion rate minus AD conversion rate is less than or equal to 5%. So the margin is 5%. Okay. There's a sample size needed to have 90% zero conversion. Tell me, first of all, do you have a data on aerosolized form vaccine? There's no data. Do you understand? So we have used only 90%, which is already available for subcutaneous arm. So therefore, this is, so the margin has been fixed as 5%. WHO wanted to have 5 in a very narrow margin. Sample size should be much higher. And this is one-sided test, 90% power, and so on and so forth. 20% dropout. So let us go and see whether we'll put that in the software. This is, do we have anything on non-inferiority trial? Same thing coming. binary outcome for non-inferiority trial. Can you see this one? Yes. Click that one. Very simple. %5. Say again. Let's see. You wanted to put 95 or whatever? No. Just no. We just say that. Okay. Let's see what happens. Maybe you are right. $617. So let us look at what we have got from the study. $617. Do you understand? This is published in New England Journal of Medicine. So
The picture is also given.
yeah, 1 minute. This is just to explain the concept. Yeah, if you have data, say for example, there's a paper in literature which says 90%, 95%, put that values, no problem. My reading is that will inflate your number. Okay, so therefore it is easy to assume that no difference between the two arms, that will reduce your number. Okay, so no, that doesn't matter, but the concept is correct. Now we are saying that I'm just giving you a clarity against there is a small difference, and therefore there will be a phenomenal number will run into thousands. Therefore, we cannot plan equivalence trial and non-inferiority trial is wrong. People don't look at that there is a delta margin attached to the calculation. You understand? That has to be explained to your seniors. So now let's say the same example, I'll just go back. Supposing 92% in the 92% in the control group, that is your subcutaneous arm. Here, 91, let's say 90%. Now let us look at the sample size. Do you understand this? It increases sample size. Why it increases? That the difference is 2 units. 2 minus 5 is 3. Denominator becomes 3 instead of 5. So therefore, there's a phenomenal increase in your number. Okay. So therefore, it is easy to assume if you have a number problem, easy to assume that the effects are same in both arms and calculate the sample size. Is that okay? I remember I'll show you that running out of time that so see this book. This is the book which I said. You can quote this book. Our studies in New England Journal of Medicine, we have approached it assuming that both are equal in effect. So this is something which you need to know. Is it okay? Do you have any questions? We'll spend 5 minutes. Yes, ma'am. Yeah. Yeah. So, yeah, yes. Yeah. No.
No, that I was trying to understand why the number 1,000.
Okay, because 900 plus we had something. Usually in clinical trials, another point which I wanted to tell you about the study is clinical trial, we don't assume that 10%, more than 10% dropout. It is okay. In the NAR study, we have put 20% because the study was done in Pune outskirts, the area where migrant population stay there. Their children were vaccinated. That time there was some political unrest. People started moving away from that area. Therefore, on the safer side, to increase the power, we put 20%. A lot of discussion that we should not have 20% dropout in clinical trials. Means the process of doing the study is not going to be good. We allow wide margin of non-response. Usually 10%. If I say 20%, 600 is a number. 6 times 120 subjects, 720. So that is how we calculated the sample size. If you look at that paper, you'll say that did I say? Yeah, the sample size needed is approximately some 800, 900 something we got. And so therefore we made it as 1,000. We studied only 900 plus something, not 1,000. I'm just putting that number. Okay. Okay, and if you don't have any questions, we will move on to sample size calculation for survival analysis. When you have time to event outcome.
So one question, sir. Where did you account for the 20% in this dropout calculation, in the sample size calculation?
No, the calculator, there's no provision for that.
Okay.
You have to manually calculate. There's no provision for that. In fact, I can't ask us to put that provision also in the sample size calculator, the software which we have developed. We don't have that provision, so we'll have to do it. Okay.
So will we cover sample size for cluster RCT also?
Which one?
Sample size calculation for cluster RCT?
Yeah, that is
We talked about it on Friday.
Friday.
Okay. Right.
There is a slide and I have, there's a link here. There's a link to calculate sample size for clustering. So this is, don't have to worry about that. Now let me go into the third part of the presentation as survival analysis. I'm not going to introduce the basics of survival analysis. This is survival function. Over time that it comes, the probability of survival comes down slowly. And so please remember this, it starts off with the 100%, over time it comes down. The corollary to the survival analysis, survival probability is hazard rate. What about the hazard? The hazard is not a probability, hazard is a rate. It doesn't fit into the range of 0 to 1. It could be 100, 200, and so on. Hazard. This is hazard function. So the opposite of probability, survival probability is hazard functions. Please remember. So we are using this concept in calculating the sample size calculation. There are two ways of calculating sample size in survival analysis. One is using the survival probability, cumulative probability of survival. Another one is using a hazard rate. Okay. So why it is necessary. Many times you look for data of hazard, you will not get that hazard. What would I do? I simply take inverse of the S of t, survival probability, use that as a hazard to calculate the sample size. You understand this? So this is some of this concept to explain to the question is how many, what is the size that we should have? So these are all inevitable things when you do survival analysis with the censoring, without censoring, and so on. Let us look at this equal allocation, survival curves with the equal allocation, which means you are dealing with the survival probability, cumulative probability of survival. It's a formula. Don't worry about this. This is the proportion of survival in treatment group, proportion of survival in control group. Take logarithm of it and do this one, you will get a hazard rate. So let's see how do we calculate sample size. So if you have any paper which suggests that survival, which provides survival curve, the proportion of survival in the first group is 80%. You fix the time. At what time it is survival 50, 80%, 70%. So at 5 years, at 3 years, and so on. When you compare it with the other group. So we have calculated the sample size based on this probability at 5 years of survival, at 5 years, at 3 years of survival, and so on. So therefore, this is very simple, as if you are doing a superiority trial with the two probabilities, proportions. Is that right? Here, there's one more concept called hazard is 2 or 3. You negotiate that. We wanted to have a hazard of 2 times more, 3 times more. This is a hazard ratio of the two hazards. Hazard cannot be, hazard is not a probability. Hazard is different for one group as compared to other group. Take the ratio of it. You hypothesize that. The hazard could be 3 times more, hazard could be 2 times more, and so on. And if you input the data, you'll be able to calculate the sample size. This is the end master, this one. The hazard rate, this is one way of calculating it. If you know the hazard rate, 0.25, this is 1.6. And so it says that you need to study 280 subjects in each arm. Okay. You can use this one, this formula. This is the one. It's a superiority trial. Do you see this? Where did you see this one, this formula in master? 2 proportions. So, but you don't have that hazard ratio concept. I think it comes from 1 minute.
Sir, in the problem, the example narration, there is no reference about the hazard rate. So does the investigator sometimes give an instance?
Yeah, you suggest that. It's like you are.
What is the meaning of that?
Hazard is not the probability. So let me say that hazard of dying, risk of dying, not risk means probability. The hazard of dying for one group is 2 times more than the other group. So that has to come from you only, the investigators.
Existing literature will provide guidance.
From if you review the literature, you will get that information. Okay. So anyway, I'll show you that one, that we put it in the software. You see survival analysis. Comparing survival curve to survival curve. This is what I have said, 80% probability of survival at 5 years. This is expected to be 90%, and hazard ratio 2 times more at that point in time. And power is 90%, alpha error is 5%. This is 2-sided test, 273 in each arm. You don't have to specify, please remember, if you do proportional hazard assumption, if you have a proportional hazard assumption, you don't have to specify at what time the hazard ratio is 2 or 3, because the hazard changing over period of time. But if you say that unless you study, I am going to do a study for 5 years or 10 years, then you say what is the hazard at that particular point in time. Okay. So what time the hazard means hazard ratio, the proportional hazard assumption. Treatment 1 and treatment 2. This is time. This is hazard ratio. The proportionality assumption which says that at any point in time, you take the hazard ratio of 2 interventions. Say for an example here, this is 2. You take the ratio here. This is 2. This is 2. Irrespective of the time, the ratio of the 2 hazards are 2. That is what you mean to say here. If you assume it that way, if you wanted to use proportional hazard assumptions and models and so on and so forth. No, it is going to change. I know about one arm. I am interested in 5-year. What is the hazard? Let's say lambda or whatever, hazard ratio, hazard. Say 2 times more, 2 times. They're asking about hazard ratio. Therefore, the hazard ratio has to be at this particular point in time. There's another arm. We assume that this is 2. So you're not worried about the other point in time and so on and so forth. So generally what I'm saying is when I said the hazard ratio is 2, it is assumed that ratio is going to be similar at any point in time. That is a very important assumption that model has. Doesn't mean that you'll have to draw it from there and use it. But you have to input the data into the analysis. Any questions? Yes, sir.
Survival analysis is being talked about, but the example which has been shown for us to understand, it is talking about how soon the bed sore is healing. So it is not related to survival.
Healing is outcome. Success or no, healed is outcome.
Okay. And
tomorrow will be.
Because sir, my confusion is what to apply when. Like hazard survival analysis, generally what my understanding has been so far is related to death as outcome or number of years the patient is surviving after.
The survival is misunderstood by many people. Survival means not mortality. So the event could be yes or no, even could be a cure or no cure, not necessarily mortality. That's why the real term for survival analysis, time to event analysis.
Okay.
We'll stop here. And if we have any questions, I'll be here. We'll discuss it as we go. Is that okay? We'll break for lunch now.